is we roll 6 two-sided dice. Well, a naive first approach, you may think, well, I've got 2 dice. The possible rolls are 2 through 12. And what did I ask for? An 8. So, I'm sure you all know the answer to this. Is the probability of an 8 1 out of 11? Because there's 11 possibilities and there's only 1 8, so is it 1 11th?
No.
It's definitely, we know that it's not, we know that some of these numbers are more likely than others. And having dice of different colors can really help illustrate this, because we know that there are actually 5 different ways to roll an 8. And this is whenever I teach this class online, this is always the tricky part. You have to convince students. Students may say, well, there's only 3 ways to get an 8. I can roll 2 6, or I can roll 3 5, or I can roll 4 4. So the different colors are really helpful in this regard. I can roll 2 6. I can also roll 6 2. Well, clearly these are different because I had the 2 on the black die for this one, and I had the 6 on the black die for the other one. So there's really 5 ways to roll it. And how many ways total? What am I dividing over? Right, because there's 6 different possibilities for the black die, and 6 different possibilities for the white die. That's 6 times 6. So the probability of an 8, this is not true. The probability of an 8 is actually 536. And some students like to see it as you can draw a chart. You can put 1 die across the top, and 1 die. I'm not going to fill in the whole chart. Fill in 2, 3, 3, 4, 4, 4. And there's a nice little pattern with diagonals. So, sticking with the dice, if we go on to number 2, what is the probability if I roll 2 dice? No, we're thinking something we don't normally do with dice. We're thinking of product. But what is the probability that the product is odd? The product is, if I roll 2 dice, what's the probability that the product of the 2 I get is odd? You can count the odd outcomes, right? Because this can happen in 2 different ways. It can be 1 2 or 2 1. This can happen in 4 different ways.
It was from some now.
This can happen in
product.
Some are product.
Oh, product. You're right. I'm sorry. I'm using the wrong thing.
No,
What about
I
that?
think you were right. 3 can be 1 and 3 or 3 and 1. Isn't that what you were saying?
But that's-
You
Yeah,
can
but I'm
roll
doing
it- you can roll it
But we're doing
twice.
product. You're right.
No, it is product. 3 times 1
Which is
and 1
harder.
times 3.
Right. So we could.
That's 2 ways to do
That's
3.
what he was not doing.
Right. So we could have a 1 times 1, or 1 times 3, or 1 times 5, or 3 times 1, or 3 times 3, or 3 times 5, or 5 times 1, or 5 times 3, or 5 times 5. So these are the 9 outcomes to give you an odd product.
But given that they're both the same, it doesn't. I mean, they're both the equal. You got equal probability. It's going to be even odd on either one dice. So you reduce it down to 2
Right.
possibilities, and so all of a sudden it becomes out of 4. And
Exactly.
So one,
And that's a much. I mean, that's really a much easier way of thinking about it. You can think of this die as being, there's 3 odd sides and there's 3 even sides. So the probability of 1 die being odd
That's a good
is a half. And the probability of the other die is also a half. And so if you can think of it like, you can almost think of it like flipping 2 coins, right? You've got a coin with an odd side and an even side. That's essentially what all we care about for the purposes of this problem is whether we roll odd or even. So the probability that they're both odd, which is what we need, is just a quarter. You can even list 4 different outcomes. And all these 4 are all equally likely, and the only one that works is the odd. So this is a way to sort of distill. We don't have to count all the different outcomes. We can just distill distill the problem down really to this essence where we only care about whether the die is odd or even. So we only have the 4 outcomes we have to worry about, and there's only one that works, so it's a quarter. Okay, let's move on to number 3.
This one under like 1, 2, 3, 4, 5, or this one.
So we've got some bag,
25 ways.
and it's got 5 red and 5 blue. And I'm going to draw 2 of them. And it's these problems, and students rightfully complain that often these problems are very kind of vaguely written. It's not often clear what's going on, but I kind of envision this as we're just going to reach into the bag, I'm going to grab 2 of them and take them out. That's what it says. It's a select 2 at random. So the question is, what is the probability we select 1 of each color? Sorry?
2 nights.
2 nights. How'd you get 2 nights?
5 choose 1, 10 choose 1 number, 10 choose 2.
So you counted, so we can count the number of ways we can choose. There's 5 choices for the red one. I think you got the right calculation, but I think you got the wrong number.
I got 5 9.
5, that's I think.
But I didn't do it with any combination. I just thought it doesn't really matter what you pick first.
Are you,
Replacement or without replacement?
just, when I was just gonna reach in and I'm just gonna grab.
Oh, yeah.
Alright.
Oh, okay, so.
Yeah, you're exactly right. That's the easy way to think about it. But we could count the outcomes. Let's do it both. Let's do it the counting way first. We count the number of ways to take 2 marbles. And think of taking them one at a time. So we've got 10 choices for the first marble. And then there's 9 left in the bag. So we've got 9 choices for the second marble. So there's 90 possible ways to pick. I'll use a little wording, say 1 and then another, because I do. There's 10 ways to pick the first marble, and then there's 9 ways to pick a second marble. Now this is a little different than what I described, because I described reaching my hand in the bag and just grabbing 2. So if I wanted to take that into account, I've got to divide by 2. I could have taken A and then B is the same as B and then A. So it's 10 times 9 divided by 2 is 45 ways to pick a pair at the same time. Now if we want to count the successful outcomes, which is how many ways to pick 1 red and 1 blue, well there's 5 different ways to pick a red, 5 different ways to pick a blue, so there's 25 pairs of 1 red and 1 blue. 25 pairs of red. If you don't see this right away, you can think of arranging them in like a multiplication table. You've got the 5 reds on the top and the 5 blues going down the side, and then each of the boxes is going to be 1 red and 1 blue. So it's 25 different pairs. And I don't need to divide by 2 here because I don't care whether I pick the red or the blue first. I'm only saying I have 1 red and 1 blue. So the probability is 25 over 45, and it does simplify to 5 ninths. But the think about it way to solve this is what you suggested, is that you can think about picking them 1 at a time. And it doesn't matter which one I pick first. Let's say I pick that one. There's going to be 5 remaining in the jar that work for me. Out of 9. I want 1 of each color. It doesn't matter whether I pick the red or the blue one. If I pick the blue one first, it'd be 5 red and 4 blue ones. So no matter what I pick to start with, I'm going to have 5 successful second marbles left in the bin. So it's going to be 5 nights. So we can get 5 nights essentially right away without having to go through all this counting. So this is the theme really of all the problems on the sheet. I'll do the last warm up and then I'll let you work on some of these. Is that they all have somewhat complicated solutions, but they also all have either relatively simple solutions or that there's some little twist to these problems. But let me go through and do the last one from the warm up section. So we've got an octagon. pick two of the vertices at random, and this one failed, because I wanna know the probability that they're adjacent, that they're right next to each other.
That's the number 42.
2-7.
Oh, that they're adjacent or one?
Two
They're adjacent, but the two we
Oh,
picked,
two, okay.
where did 2 sevens
2 sevens, yeah.
come out?
This is one where it's also possible to just realize the first one doesn't matter.
Exactly, it's the same as the one we just did. The first, you're picking two, but because of the symmetry of an octagon, the first one, you can think of picking them one at a time. This is a very common little probability problem-solving gadget. It's just because the problem seems to imply that you're choosing two at once. If it doesn't really change the problem, you can think of it as doing them one at a time. And usually that's an easier way to think about it. So here once we pick the first one, it doesn't matter which one the first one is, because the whole thing is symmetric. They're all the same for the purposes of whether we get an adjacent pair or not. And once I pick the first one, there's going to be 2 of the remaining 7 where I win, and the other 5 fail. So the probability is just the 2 that successfully work over the 7 possibilities. Now you could go through all the counting. You could count how many pairs of vertices there are. Well, there are 8 times 7 over 2 pairs by the same logic we used with the marbles. There's 8 choices for the first vertex and 7 for the second. We divide by 2 because we think of picking them as a pair. So this is 28, and then you can clearly see there's 8 sides that work. So the probability is 8 over 28, which is the same 2 sevens. But this is a way you get the answer essentially immediately. So let me let you work on,
6 choose 1, 6 choose 1, 2 choose 1.
I would suggest if these types of problems are less familiar to you, work on 11 through 13. And if you feel like you're this is a pretty well-known area for you, then start thinking about some of the ones in the 20s. And I'm going to talk about some of the problems in the 20s. Some of them are fairly famous problems, and they have lots of interesting twists to them. So take a look through these problems, pick your favorites.
I hate when my kids are like, isn't it 75 over 4,205? And I'm like, I don't know. Can you show me? They're like, I didn't get that. I got 47 over 9,205. I'm like, yeah.
What did you say? You said something, choose something.
So I think of it so out of the 18 people, 14 people, right?
You said 14 choose 6?
No, 6 choose 1, 6 choose 1, 2 choose 1. Because out of the 6 Democrats, you're taking 1. Out of the 6 Republicans, you're taking 1. Out of the 6, you're taking 1. And then all over, 14 choose 3. And then 14 choose 3 is the total. So there's the denominator. But so can you explain why? So what Alex is 6 over 14 times 6 over 13 times 2 over 12, right?
How many different committees you'll get.
A?
So
Before I
he's
forget,
putting
I'll give these to you. These are the answers, and give out some later data.
Do you have PDF files of those?
I can send it to you.
If you did that, would you be okay if we posted them on the NAMC website?
Oh, certainly.
Problem Centers?
Absolutely.
So we'll do that along with the video.
Okay.
I think Randy's saying to put them on the BACT website, not on the NAMC site.
We can put them on both. I'm really trying to build.
Dave,
Yep.
do you know what number 11 is?
I know what number 11 is, yes.
You get a different answer. You get 6 over 91 instead of 18 over 91.
I got part of that.
For which one, part A?
I want to look at 11C.
C, yeah, like 18.
Right. So it's because you're putting your choices in.
18 is, C is a little different.
See, I got,
Depending on how you count it.
Yeah.
yeah.
I should got it.
It depends on how, you can do it several different ways.
I'm going with the.
I don't know what I'm missing.
Yes.
So that counts.
considered with probability
Well, that's what
without counting.
That is counting, say, like,
I did that.
Republican
Did you do
first
that?
and then
So,
Democrat.
we're
I just did.
What's the
Right.
probability of
Right.
one with
Democrats
Republican?
first and then
That's
Republicans.
6 out of 14. What's probably you pick another Republican for that's 5 out of 13.
in the beginning,
Next thing,
come up with
4 out of
ideas.
12.
Here's a
That's,
triple.
that's 5 out of 13.
I did it, I had exactly the
They're
same
already on
numbers,
the
but I figured out what are the
What is
12
probability?
possible
Yeah.
permutations and
Yeah.
then
So your answer is 1/3 of what it should be.
Right, I get that.
it's exactly the same.
Yeah, once,
Yeah, that's what I'm saying, multiple.
because there's
ways.
6, like it's like 3 times 2 times 4.
Yeah, this is, I'm gonna mention this.
I feel like
because
multiply
I think
it
a lot of
by
people
the
get in this.
number of ways I can
this issue
make that
and
much.
It's,
You know, it's like
it's
2
what I
ways
call
to
the
the
apples
first
and
selection.
oranges issue.
But still, that's
So probability is always a numerator and a denominator.
I feel like it's-
So you've gotta pick, like sometimes in a probability problem, you'll have a choice as to how
If
you
you were
decide
telling
to count
someone
things.
else, out of these 14
And it's okay as long as you don't compare apples to oranges. So as long as you're consistent. And usually the consistent choice is, do you pick,
this person can succeed.
do you pick in order, or do you pick without caring about it?
Like those are different individuals. Like they can. You're saying
And so it doesn't, in most problems, it doesn't matter which one you pick. You can do it in order, or you can do it without caring about the order. But as long as you do the numerator and the denominator the same
that's
way,
like saying
it's
it's okay, you
fine.
might end up with the same thing.
But that's the tricky part, is you gotta do
So
the
let's say
numerator,
you're paying
for
me to
example,
randomly pick a committee. Before I start picking, you're telling me that I have 6 out of
we were looking at
14
11C,
getting first.
right? You have to decide if you're gonna pick any of the 11. You're gonna pick this 3-person committee.
14.
Are you gonna pick them one at a time? The first guy, then the second guy, then the third guy? You're gonna pick all 3 at once. It doesn't really matter which way you do it, as long as you do it consistently, numerator and denominator. That you pick. So you're counting successful committees over possible committees. You have to be consistent with whether you're picking them in order or without caring about the order. And parts A and B and part C are a little bit different in that regard.
You really need to count those.
You definitely don't necessarily have to. Well, C is a little tricky, that you try to do with.
Well, I got a choice. To get a Republican, I got 6 out of 14.
Uh-huh.
To get a Democrat now, I got 6 out of 13.
Right.
And you get an independent, I got 2 out of 12.
Right. But you could have picked the Democrat first and
Doesn't matter.
still been successful. It does matter though. That's the tricky part. Because all you counted was, you counted the chances of picking a Republican first, then a Democrat, then independent.
No, multiplication is commutative.
Right, but you're
Doesn't
not,
matter.
but the fractions don't represent the same thing.
No, but the answer does.
This is good. This happens all the time. This is why probability is tricky, because this is not the correct answer, but it's hard to explain in this sense. Let me see if I can explain it.
Wait. I've got 3 fractions multiplied together.
So here, let's talk about 11C. So I've seen a couple of people do this. They claim that
I started with that same approach.
6 times 6 over 14, this is a Republican. Because there's 14 people to start with and 6 of them are Republicans. You've got a 6 over 14 probability of picking a Republican. And then for your next step, you're going to try to pick a Democrat. So now we've got 13 people left on the committee, 13 people left in the pool, and 6 of them are Democrats.
And once they got the probability that I'll choose out of the.
So the last person is an independent, and there's 12 people left in the pool,
Uh-huh.
and 2 of them are independents.
The order doesn't matter, so now you gotta multiply that times how many different ways you can arrange those.
But if you do that, you have to divide, you have to.
Yeah, it's just like the dice, right?
Right, exactly. So what you,
When you
basically what you've done is you've computed the probability, say, if we want to do the probability of rolling 11 on the dice, what you've computed is the probability of rolling a 6 and then a 5.
Can I try?
But then you also have to do the probability of rolling a 5 and then a 6.
But look at the problem. I could move my numerator something.
Here, can I?
Go ahead.
So, like, what this represents is this represents the probability of picking a Republican, then a Democrat,
Oh, you're right.
then an
Exactly.
independent.
Right.
In
So
exactly
I've got
that order.
And so
But it's a
multiply by
committee,
6.
so it doesn't matter how many, it doesn't matter the order in which
So
you pick.
multiply by 6.
Exactly.
Yeah.
So this is
Yeah.
this is answer is off by a factor of 6.
Yeah.
But
Yeah.
don't you have to, okay, I think of it a little bit differently, because if you calculate the total possible committees you can form, and you do 14 choices for the first one,
I'm just cleaning this up just so I, okay,
so
go ahead.
14 choices for the first one, 13 for the second, 12 for the third, but you can arrange each of those numbers in 3 factorial ways, so you divide by 3 factorial.
So this is the number,
That's the number of total possible.
possible committees.
So then when you do your numerator as well, you've got 6 ways to choose the first, the Republican, 6 for the Democrat, 6 for the Independent. Don't you also just divide that by 3 factorial? Because it's a committee and the order doesn't matter?
But when you did this, you didn't, there's no choice of order in here. Here there's a sort of a choice of order. You're picking the first person, and then the second person, and then the third person. So there's sort of time was involved in that. Those were ordered according to time, right?
Okay.
These were not ordered according to time. We picked one from this pile, and one from this pile, and one from this pile. We don't care, we don't know which one of them is first, and which one of them is second, and which one of them is third. That wasn't part of this calculation.
But we know we've always, it doesn't matter that we always have 6 Republicans to choose from, 6 Democrats, and 6 Independents to choose from. So it doesn't matter whether we chose from the Independents first,
Right.
or the Republicans first. or
That's
the
correct.
Democrats.
Right.
So if we, it seems to me we should be dividing that number by 6 rather than multiplying by 6.
No, look what you've done.
No, it's the 6
See, if you have
Republicans.
14, 13, 12 divided by 3 factorial is multiplied by 3 factorial, right? You
No.
have 6, 6, 2.
No, he's not gonna multiply that one by 3
There's,
factorial. No, he's not gonna do that.
But this would be back here.
If he did that, he'd get the answers we got.
No, but look, if you take the total number 662, that's cool. Divided by 14, 13, 12 over 3 factorial, you get what he ended up there,
Oh,
3
That's
factorial.
the correct answer.
Okay, yeah.
I mean, the point is that this one, in this calculation, we do divide this by 3
Now
factorial.
I'm happy. Yay!
Oh, right, we have to.
We understand this problem, we understand the problem.
If you don't want to, that's one specific.
Thank you. Yeah.
Yet another way to look at it, I'm gonna keep this problem in the ground because it's such a indicative problem of the issue and probability. Just imagine we have a table set up for our committee. We've got the 3 chairs at the table. So if we're gonna think of it as an order table from left to right. So we've got, we just look at all the possible committees. There's 14 choices for people here, 13 choices for people here, and 12 choices for people here. If we're gonna try to do the 1 Republican, 1 Democrat, 1 Independent method, we first pick the 3 people. We've got 6 choices for the Republican, 6 choices for the Democrat, and 2 choices for the Independent. So that's step 1. And then step 2 is we take these 3 people and we consider this table. So we've got 3 choices for which of these 3 people sits here, and 2 choices for which person sits here, and then 1 person for which person, we want 1 person left in the last seat. So the denominator is 14 times 13 times 12, and the numerator is this 2-step process. It's the 6 times 6 times 2 for picking the committee to begin with, and then a 3 factorial for taking them and setting them at the table. So this is, I don't know which is the apples and which is the oranges. This is the apples way, I guess. We worry about the order that the 3 people are on the committee, and this is the oranges way, where we don't worry about the order, we just worry about picking 3 people. So that's why we divide by 3 factorial in this case, because we picked them in order, and we don't want to care about the order in this calculation. But when we pick them like this, there's no order there. And I agree, it's very confusing, and if you're confused by this, you're not alone. But this is the difficulty in a lot of these probability problems. Is apples and oranges. Is that you have to be consistent with when you're counting successes, when you're counting possibilities. You have to count them in a consistent way. If you're going to care about the order, then you have order for both parts. If you're not, in this case, this is one where I don't care. And they come out with the same answer, and you check the 3 factorials, I mean, this one comes out to 6 times 6 times 2 over 18 times 13 times 12, 3 factorial. So it's the same thing. Yeah.
I'm a complete novice at teaching probability. I haven't done it for very long. But what I found is that if my students get confused on this a lot,
Yeah.
I find that if I actually am very strict about using the combinatoric notation, the n choose r notation, when I'm doing counting, if I'm
Right.
very strict about that, and I use the success way, it helps the students a little bit differentiate between the two.
Yeah, definitely, like, when I do this in class, I didn't do this, sometimes not everyone is familiar with the notation. But this is written as 14 choose 3. This type of counting computation is 14 choose 3. We're picking 3 items out of a set of 14, and we don't care about the order. But it doesn't quite work with this. I mean, you could write it as 6 choose 1 times 6 choose 1.
Exactly, that's
times
what,
6
yeah.
choose 1. That actually probably is a good idea.
All over
We're
14 choose
We're
3.
picking one of the Republicans and one of the Democrats
Right.
and one of each. Are we looking for the solutions?
Yeah, the solution.
Josh, I gave them to Josh.
Oh, Josh.
Josh is
I was trying to withhold until a little later, until we had worked through
So
some of
you
the
were
problems.
successful
Yeah.
because you handed
He
shit.
obviously walked off with them.
Yeah, absconded.
I do have written solutions for most of these problems, and most of them have explanations.
Yeah.
But I really did not want to. I didn't want to give them out because I didn't want to spoil some of the problems in the 20s because they're fun to unspoil. But I do have some tools for all of you.
I went for later, but the other one is the way we're here. The top one. That one you multiply what you normally would do by 3 factorial.
It doesn't matter what you get on the first one.
Okay, we figured the change.
So it's like 3 out of 91.
I try to do it that way. That involves some casework, so I guess that was more like this approach. It definitely, think of doing it one at a time. You're right. Any first person you pick is going to work out okay. And then if you started with a Republican, there's only 8 people left.
You know, like the birthday
If you
problem?
started with an independent, there's 12.
That's where the chair method is. That
Yeah.
is
So like,
that's
so
that.
the chance that you and I have the
You
same
can do it that way.
100%.
But I think for a problem like this,
In order to get 50%.
trying to build it totally more straightforward. You could do it
23. Which, so it doesn't stack as your basically when you think about like people are not following minutes.
Why do you get 3 factorial on that one?
You could say,
And then divide by.
No, on the top,
It
it
doesn't
doesn't mean multiplying times 3 factorial.
Yeah, the top one, because that's.
And then also there's like that whole thing. I just leave the pitch that
The top one is a lot.
you could start with,
So the top one is.
Oh, is it?
The top one isn't.
So you can't just say
Then you
6
can
over 14
you could start with if you,
6 over
well,
13.
you have to do this in all 6 different orders.
That wouldn't get you right
Because
answer.
the number of people you have available for each step depends on whether you took the
So we're at number 21.
The property.
That,
You know the
that's
answer?
something we know. It's just like it would be the same for each slice of time, you know, 9%.
So.
No, that can't be right. 'Cause if you have a 90% chance of fishing a fish in an hour, but you go fishing for like 2 seconds.
We did it at the end of the year.
I got a better example for that though. If you have a 90% chance for 1 hour, you don't have a 180% chance for 2 hours.
Right.
It's not linear like that. That's not what uniform, uniform means that you have the first, same as, chances in the first 10 minutes are the same as the chances in the last 10 minutes. Same as the chances in any middle 10 minutes you pick, just that we accumulate it all in an hour, it comes out to your 90. sophisticated.
Okay.
It just requires the right way of thinking about it. The theme of most of these
Word
problems.
has one word. This seat, the way the seat is 14, 13, 12. On the right hand side of the board, and then below it has 3, 2, and 1. Right? 3 choices, 3 choices, and 1 choice.
Oh, right.
Right. The question next to it is, what's on the
Well, I guess you
numerator?
could
6 times 2?
Yeah, let's talk about people are talking about the fishing problem, which is 21. I think I'll leave.
That's how
I'll
many
leave,
you teach that you're able to.
I'll leave 12 and 13 for homework, or we'll come back to them a little later. Let's go on to the fishing problem, which is probably one of my favorites on here.
Which problem?
Number 21, the one with the fishing. Kenny is gone fishing. This also partially, this problem goes a little bit to the meaning of probability. It goes to not jumping to conclusions. There's all sorts of great problem solving lessons in this problem. So she's fishing for an hour, and we're given this bit of data that there's a 90% chance that she catches a fish during the hour because it's a well-stocked lake. And what uniform the entire hour means, we were just talking about this, I don't know if you heard, but it means that it doesn't matter what 10 minutes we look at. So the chances in the first 10 minutes are the same as the chances in the second 10 minutes, as the same as the chances between 33 and 43 past the hour, as it is the same as the last 10 minutes. It doesn't matter what slice of 10 minutes we're looking at, that probability is always going to be the same. So the fact that I asked about the first 10 minutes, it could be any 10 minutes I could have asked about. So a very common misconception about this problem is that, well, gee, 90% for an hour, 10 minutes is a sixth of an hour, so it must be 15% for 10 minutes. And my retort to that is, do you think that if she fishes for 2 hours, her chances of catching a fish is 180%? That obviously is not, that's an absurd thing to say, so it's not quite that simple.
Yeah.
Yeah, when you actually get the final answer, a calculator is going to help a little bit. But I'll just tell you what it is too. When we get to that point.
I'm guessing you probably want that.
Is it 90%?
That's not it.
That's your guess,
So
yeah.
it seems like if the probability is constant,
I feel like it's gotta be something else. Yeah. Yeah.
Let me ask this question.
Sounds like it's-
Why is that logic absurd? Just, I mean, the answer is absurd. Like, if you fished for 2 hours, we know the probability of catching fish is not 180%. Because that's absurd. Probability can't be more than 100. But why doesn't that logic work? I think if you can answer that question, then that explains a lot about this problem. Why do we just not?
She might not get fish either hour.
Right, she might not catch a fish.
but you're adding the probability.
What is it? Let me ask you that. What is the probability? If it's 90%, so the probability of a fish in 1 hour is 90%. Well, I'll write it as 0.9 because what is the probability she gets a fish if we let her fish for 2 hours?
Actually, maybe.
It's a 99%.
Explain why that is.
Well, I mean, I just work backwards, which is what's the chance that she's not going to catch the fish in either hour?
Exactly.
110 times
Right.
110.
Right, that's exactly right. The probability of a fish, catching a fish in 1 hour is 90. So that means that the probability of no fish in 1 hour is 10%. That means the probability of no fish in 2 hours is 10%. If you don't see why that's true, go back to, again, my favorite example of the dice. The probability of 1/6 in a die is a 6. The probability of 2 sixes is a 1/36. You have 2 events, you need to have 2 events both happen. You multiply the probabilities. So if I need no fish in 2 hours, I have to have 10% happen that she doesn't get a fish in the first hour, and I have to have the 10% happen again that she doesn't get a fish in the second hour. That's only going to happen 1% of the time. So the probability of fish in 2 hours, what's left over, is 99%. So that's the mathematics of it. Is there any sort of done like this, besides? This is a little harder to explain. I mean, the way I think about it is that the probability of catching a fish in 2 hours, there's sort of multiple things that can happen. She might catch a fish in both hours, she might catch a fish in the first hour and not the second. There's just too many different cases to worry about here. But if you look at the opposite, there's only one possibility. The only way to not catch any fish at all in 2 hours is to not catch a fish in the first hour, to not catch a fish in the second hour. So that's you always want to try to set up a calculation that's as simple as possible. So now how do we use this? Well, we need to answer the question in about 10 minutes. I'll write it as a sixth of an hour, because that's obviously the mathematics we're going to need. Well, to go from 1 hour to 2 hours, I squared it. What do you think I have to do to go from 1 hour to a sixth of an hour?
The sixth of, is that like,
Exactly.
is that like this?
68%.
Probability of no fish in a sixth of an hour. It's the same logic. 0.1 to the sixth, and the sixth would be 0.1. You calculated it right.
68%.
To the nearest percent, it's 68%. So to go back to answer the original question, 32%. So this is the problem. Again, if you didn't think about it a little bit, I mean, when I do this problem in class. I mean, a large number of the students immediately say 15%. Even though they should know against their better judgment that I wouldn't ask them such a simple question in several weeks in a class like that. But and the follow-up is, well, how many in 2 hours? And so this is I think I spent a whole section of the book just on this problem. It's such an illuminating problem. It's one of my favorites. So let me. So you can keep working if you wanted to try 12 or 13, which are, to me, less interesting, but the ones on the back, 22. And then you're going to try to explain it. I've never heard a really satisfactory explanation. But it's a very famous paradox in probability, and I've got to use a particular set of numbers. So we're going to play a game. And if you want to be more melodramatic, sometimes this is free. It's like you've offended the king, and he's either going to sentence you to death or let you go free, depending on whether you pick a green or a red ball. So we've got 2 jars. I'll call them A and B. And the goal is green is good and red is bad. So this one has 5 green marbles in it and 6 red marbles. And the numbers are slightly between. You can only make the green is good, red is bad. It's like at the traffic light. And so in B, you're going to have 3 greens and 4 reds. And so the way you want to pick a green one. So you get to choose whether you pick from A or B, and then you're going to reach in and pick one at random. And if you get a green, you win, and if you get a red, you lose. So which bin do you want to pick from, A or B? Right. A is the probability of winning. A is 5/11, and the probability of winning from B is 3/7. So if you check, put them both over 77, you get 35 here. You get 33 over 77 here. So A is better. Okay. In bin C, we're going to play the game again. 6 green, and 3 red. And in bin D, 9 green, 5 red. Same game. You can choose either C or D, but you want to maximize the chance of you picking a green.
C.
So we've got 6 9s here, and we've got 9 14s here. And if I arrange the numbers correctly, 2/3 is bigger than 9 14s. Yes, so C is better. So now we're going to play one more time. We're going to combine pins A and C. Got 11 green against 9 red. We're gonna combine pins B and D. So I've got 12 green against 9 red. And I don't even have to write down the fractions because when I combine them, there's an extra green. So how did that possibly happen? If I play A against B, I want to pick A. If I play C against D, I want to pick C. But when I combine them, it flips for some reason. And the mathematics of this computation is irrefutable because it's just arithmetic. I've not heard a satisfactory explanation. I mean, aside from the obvious the mathematics works, but sort of a philosophical explanation for how this could possibly happen.
Because A and C are very close to each other, there's a difference of 3 and a difference of 1. And B and D, there's a difference of 4 and a difference of 1. So the,
Okay, but this is still better in both cases.
yes.
I'm not disagreeing with you. I've just never heard I've never heard an argument that convinces me. So I mean,
Because if you win a bunch of games by a big margin and then lose a bunch of games by a small margin, depending on your scoring system, you may end up at the top of the heap.
but I'm never losing.
It's okay.
If I win a bunch of games, then I win a bunch of other games, and I combine them, how can I possibly end up?
You win by little bitty points.
But the difference between the number of marbles in B and D is much greater. There's only 7 in B and 14 in D. So the number when you combine them,
Do that. There's 11 here.
yeah, those are much closer.
7 here and there's 14 here. Well, why should that make a difference? I mean, this one is bigger. This one is bigger than that one, and this one is smaller than that one. But still, we sort of feel like A is better than B, and C is better than D. So when I combine it,
Does it have to do with like a weighted, kind of like a weighted average?
it is. I mean, that's closer. I think. Yeah, that's an explanation. Is that I mean, the real world. I think this may have actually occurred one year in baseball where somebody had the best batting average before the All-Star break, and the same person had the best batting average after the All-Star break. They didn't win the batting title for the whole year.
Jim Paulus talks about that in his book, in Numeracy. He talks about the column of averages.
You can't just combine two separate things like this. I still don't feel like internally I believe it, but I mean, it's
So I feel like you hear examples of this, like, in real life where you have, in a, say like in a school district, you have 2 different subgroups improving their test scores, but then the overall district, its test scores go down because the representation of those subgroups has shifted over that.
Right. But this is just something I've always found with basic probability just to be mind-boggling a little bit, even though it's just arithmetic and the data is. It's just we have one more example, which is kind of the theme for a lot of the problems today. The probability is not. It's often very unintuitive. Like we've been doing with Monty Hall and a lot of these problems. It really is a good subject for trying to teach problem solving because it's just not. There's not one algorithm you can use. There's not one method. You really have to think about each and every problem kind of on its own. And try to figure out what the relevant data is, what the relevant assumptions are, and often the answers are quite unintuitive. So I gave Josh the answer sheets and he left. So, but he'll have them tonight, I guess. But I do have the answers, and I have little explanations written up. In some cases, very little explanations for all of these problems. We didn't talk about 26, which is also one of my favorites. Let me see, were we talking?
Yeah.
Yes, we have time. I do have a plane to catch, but we've got time.
So we'll do the plain one.
So yeah, we'll do the boarding pass problem before I go to the airport. That's a good idea. So this is the one that I probably saw in other sources too, but I heard this problem on Cardlot. Does anybody know the problem? Does anybody have a guess at the answer? 26. So there's this plane, and I don't know how this happens in today's TSA controlled airport environment, but at some point between when I checked in and got on the plane, I lost my boarding pass. Well, I flew Southwest up here, so this wouldn't apply. But, I had an assigned seat on a 137 seat plane, and I lost my boarding pass, so I just took a seat at random. And then as people came on behind me, they either took their assigned seat, or if they found their assigned seat occupied, they took a seat. The probability is when this whole thing filters out down to the last passenger, what's the probability that she actually sat in her assigned seat? So the hint for this problem is try it on a puddle jumper plane with few seats first before you try it on the 737 with 137 seats. Second hint is that whenever you see a problem like 25 or 26 with a big number like 2011 or 137, that big number is probably irrelevant to some extent. That there's probably a simple formula, and you don't have to brute force 137 different cases. The third hint is, I'll let you think about it for a few minutes. You haven't looked at it before.
Possibly in the wrong seat.
Right.
Yeah, 50%.
Yeah, because it's such a
Chance that you're in the wrong seat. Right.
So we're gonna have a
Because you're either in the right seat or the wrong seat.
So let's have a two seater.
Well, you sat in. Right, but we're looking at all different sides on the plane, because we can't just look at
Most of the
right,
time,
right.
I mean, most of the
Everybody
stuff,
else would pick the right seat.
you pick
Right.
Except,
Half of
I mean, what's your chance of our seat?
can't take credit for it.
I'm off.
So
He
randomly
he's not sitting.
It doesn't, I wouldn't even say office.
Right, well, he's not sitting in her seat because.
So there's two, so
young person who's in
How
the,
to
could be in
It's
the wrong
more likely
seat.
to the fact that
But that was
these
my
numbers.
question.
So he started
What is
this
it, 511
chain,
what is
he
it?
started
They
a
said
chain reaction. He wasn't allowed to see.
These numbers are very
There's a
close.
chance
He started a
that
chain reaction of
somebody else.
These
Other
numbers.
people
other
having to
people
take
Has
having
to
to
has to
take
do with the fact,
Another
kind of averaging these numbers, but not really. It has to do with the fact that
So the last person isn't necessarily the person who's
we all
gonna
know
be
that.
sitting.
We just don't always do
It's
this.
one of the
We all
other
know
seats
that.
that somebody else.
If
sat.
they found their assigned seat.
But this is kind of what you're doing when you do the same thing that you're taking.
He is sitting in someone else's seat because people started sitting in the other seat because
So we're
they
kind of
found the
doing,
seat
we're
occupied.
kind of doing this in a legal operation. We combine, simply combine these two cases.
Right.
Sort of just.
Yeah, then I took another seat.
So whoever was supposed to be in his seat came on board and didn't say anything, he just sat somewhere else. And then, so they were sitting in somebody else's seat, and somebody else came on board, and so it could happen a few times.
Okay, so
Well, if
means there's 13 people who are gonna sit in the right seats.
If everybody sat in their assigned seat, that's what confused me. Because if everybody sat in their assigned seat, then you either sat in their seat or they're sitting in your seat.
There's
That person
always
that
like
doesn't have
this
a choice, you know what I mean?
Right, so
There's two seats,
Yeah.
These are the two seats to
and
the
it
left.
keeps
Yeah,
bifurcating
so
one of them is either
But you're gonna
yours.
either sit in the right seat or the wrong seat, but then everybody else is sitting in the right seat.
Right, so there's two seats.
Did you figure out
Right,
the
so
point?
they're
So
yours.
one out of two seats, you only got, if you get it right, you cool, if you
I
don't,
was-
then it's
no, I
only
didn't.
two seats.
Yeah, because there's only two seats you're worried about, not
I
everybody
feel like
else.
that is
Everybody
like
else found their seat.
Yeah.
missed, why kids don't
So
understand that
if you sat in
You
that
say
other
like
person's seat,
5'11",
then they're sitting in
5 out
your
of
seat,
11
or
are
vice
boys.
versa. So you only have two seats
I
left.
think it only matters
The
if
other
everybody's
one,
together.
37.
Okay.
Doesn't work for
boys.
me, I don't think.
Amazing.
You have four.
I just disagree. The thing that confused me was this line.
Right, that's correct.
As passengers board, they naturally took their assigned seats unless they have.
That just brings up the complexity of appropriation.
So that confuses me because, so then I started thinking, either everybody, the other passengers, or the other passengers sitting in the
You're
center.
right, yeah, they could.
That's,
I
that
think
line
I
right
would
there.
lean towards
There's
that.
only
Think
one
about it.
person.
Logically, but I don't think that
No, it doesn't work for
I
me.
know, but why did they put that sentence in there? Why did they put that sentence in there?
because there's only one seat left, what are their chances that the one out of 37, one out of 137 seats was
So
the
you
one
got,
left
what
over?
did you get for three?
Even if they take their
More than probably
assigned
way
seat,
more substantiated. than it's
assuming
been.
the other
Depends
passengers.
There
how
would
you
be
think
more
it-
people
depends what
sitting
you're
in the
calling
right
possible.
seat.
There's only one seat there.
And then there's only.
Has
one
anybody
seat
done it for a
left.
very small plane and gotten an answer?
You got your seat.
What'd you get?
Oh, I got the actual answer.
Oh, you did?
I think so.
But
Alright, well, we
now with the other
keep it
passengers.
secret for a minute.
Okay, we wanna hear.
Actually?
It's what, it's
The
chance-
actual
what's
one?
the chance
Not
they
the
got
pretend
there?
one?
No.
Just a guess?
Can I explain to you?
You can explain, yes.
Did he say no?
He liked
to listen to Dan.
So,
Gary's gonna convince me that
oh, I got it wrong.
I know, but you're gonna convince
So
me.
I did,
Okay.
the only way that the last person can come on and find their seat occupied is if every single person before them missed their own seat.
That's not true. Think
No.
about that for a second.
Because,
Because
the fifth person
could
could
come in and the original person would be sitting in their seat.
Let's do it.
It could be like five
Small
people.
airplane, three seats.
Well, I mean, not miss their own seat, I mean,
They
missed
just
like,
happened.
missed the seat that was assigned previous to them.
No.
Okay, let's say,
I said 136.
Let's do a three-seater plane. So seat A, B, and C. Let's say, let's say we board the plane, and I had A, and the person behind me has B, and then the person coming last is C. Okay, so there's three equally, so I'm A, but I lost my boarding pass. So there's three equally likely possibilities, right? I pick A, I pick B, or I pick C. Now if I pick A, if I happen to pick A, everybody's cool. 'Cause, you know, I pick
That's
my
your
right
seat.
seat, we're happy. So that's the happy case. Now, if I pick C, we're doomed. There's no way C is gonna be left empty, right?
But just because you put A,
That's not a big.
No, if I pick A, we're good, because everybody else has their boarding pass, they're just gonna take their seat, and everything's gonna work out. And if I pick C, we're doomed, because I've already taken, the goal of the problem is for a person in the back of the line to get the correct seat, right? So if I pick C, we're doomed. But if I pick B, what happens?
Well, there's two of them.
Exactly, now it's 50-50, because I pick B. Person B comes on the plane, sees me in their seat. They're gonna pick either A or C, right? 50-50. So it's a half chance here. So we've got one case where we're definitely gonna win, we've got one case where we're definitely gonna lose, and we've got one case where it's 50-50. So if you sum all these up, it's 50-50 overall, right? Because in this case, that's a definite win, and that's a definite lose, and then that's a 50-50 case in the middle. So you could even, you could write down, if you wanted to sum up probabilities, this one is a third, and this one is a sixth, and this is a zero. So it adds to a half. So for the 3-seat case, we get probability half. Now you can do the same argument with a 4-seater plane. A, B, C, D. Now there's more. Well, let's just work through it and we'll see if we learn anything. So there's 4 cases. Let's start with I pick A, I pick B, I pick C, I pick D. And the 2 extreme cases again are easy. If I lost my boarding pass but I happen to pick my right seat, then we're happy. Everybody else is just going to fall in line. If I happen to pick, the last person wants to get a seat, the correct seat. So if I happen to pick the bad seat right away, we're doomed. Now what about those middle 2 cases?
the third, so
They're-
B comes in.
They're maybe a little more complicated for 4. Now, first of all, I can it doesn't really matter if I pick B or C, whatever, well, maybe it does matter, actually, I shouldn't say that, because B is the next person. B, we have a problem right away, and C, we don't have a problem until one more person. So now B comes in, and you might think, uh-oh, B, I've taken B seat, so B might pick A, and B picks C, or B picks D. And what happens if B picks A?
We're all good.
C could go sit in C's seat.
Everything's
Good.
good at
Pick
this
A
point.
is good.
B picks A, well, I've taken B's seat, B's taken my seat, but then C and D are empty, C and D get on the plane, everybody's happy. And the same thing, if at any point in the process somebody picks D, we lose. What happens if B picks C?
Then
You have to wait and see.
C
So
shows
A-
up.
A picked B, and B picked C. C shows up. There's only 2 seats left. And that's the happy case. And that's the sad case. And we could do the same thing with this case. Do we have a conjecture at this point, though? It seems like no matter how I do the casework, I start, this is really big casework here. No matter how I do the casework, I always end up with a 50-50 chance between a happy case and a sad case, and there might be other cases in the middle, but at some later point it led to a 50-50 chance of a happy case or a sad case. So you might conjecture that it's always 50%, and so
Because you can answer your seat or it's
step
not.
that I would, I guess, leave for you to think about this evening is this a true conjecture or not? And if it's true, can you convince yourself that it works for the 137 seat plane? And if this is a bogus conjecture, can you figure out where the flaw is and figure out what the answer should be?
This is a bogus conjecture.
I'm trying to figure out what is how you. First one I understand.
Okay.
And now I really do have to go catch it.